Now I can start, right?
Yeah, go ahead.
Good morning, everyone. Today I am going to discuss about reciprocal space, thinking in a reciprocal space. As already we know that the crystal structure, crystal directions, axes, and crystallographic planes, unit vectors, and interplanar spacing. Everything is defined in real space. Now today I would like to discuss about reciprocal space. Here I am going to discuss how to define reciprocal lattice vectors and what are the properties of reciprocal lattice vectors. Then how is the relation with respect to diffraction, world sphere construction, reciprocal space. Yeah, even though we are having crystal structure and crystallographic directions, planes, unit vectors, and interplanar spacing in real space information, we are going for reciprocal space. Reciprocal space means looking for the same information, same fundamental science, and everything is same in different framework or different dimension, where the dimensions of quantities are one by length or length inverse is called reciprocal space. It gives the exact relation interaction between the electrons as a waves and the 3D periodic arrangement of 3D periodic structure of a material, and especially it gives the much more information clearly when we are studying diffraction as a tool for material calculation. Here A1, here A1, A2, A3 are three unit vectors in real space. Here I'm considering one triclinic cell. We are defining reciprocal lattice vectors. We are defining as per our convenience such that it will follow some properties. Here we are defining these reciprocal lattice vectors B3 such that this B3 vector is perpendicular to A1 and A2. Here A1 cross A2 means this area of this parallelogram OAMB. So B3 is perpendicular to this plane. So this B3 is perpendicular to the vectors A1 and A2. We are defining such that this B3 is perpendicular to A1 and A2, and B3 is having a magnitude of 1 by length or quantity. The dimension is a 1 by length or length inverse. Similarly, B1, B2, we are defining these vectors such that it is perpendicular to remaining A1, A2 and magnitude of 1 by length. So what is the B3, magnitude of B3? So to find out that we define B3 as a cross product of A1 and A2 divided by volume. Here volume is the volume of the unit cell. It is a scalar quantity. From the standard definition of cross product, A1 cross B or A bar cross B bar equal to, it is perpendicular to A and B, and here it is equal to the magnitude of this area of parallelogram. Here we can see OAMB. Therefore, magnitude of B3 bar equal to area of OAMB and divided by volume of unit cell. Here volume of unit cell is nothing but this area and perpendicular distance between these two planes, which is equal to H, it is equal to OP. Therefore, B3 equal to area of, we get this 1 by OP, it is equal to, let us consider the this OP is equal to the interplanar spacing between these set of parallel planes. So in case of B3, it is equal to the interplanar spacing between set of D001 planes. If it is D001 plane, it is going to be 001 plane, and below one also there is a 001 plane. So therefore the
So
magnitude of
one
B3,
minute, I didn't understand this OP. So A1 and A2 are in one particular plane, right? So what is the distance between OP? How do you measure?
this OP is the projection of A3 vector on B3.
B3 on B3. Okay, so okay, you're considering all three vectors, A1, A2, and A3 also.
Yes, this is the perpendicular distance between these two set of parallel planes. It is equal to the projection of A3 vector at C on B3 vector. It is equal to the OP. It is equal to the perpendicular distance between these set of parallel planes. In standard notation, we define that it is the interplanar spacing of D001 planes.
Okay, that's fine. Then what about this volume? Is the volume of the cell A1,
Yes,
A2, A3 vectors or something like this?
you
Is
see
it
the volume of the unit cell is volume equal to a1 dot or a3 dot a1 cross a2. It is equal to area into perpendicular distance of this is unit cell volume is equal to length, width, height, right? So it is
Yeah.
equal to area into perpendicular distance height. Therefore,
Okay.
this
So
perpendicular
no, no.
distance is
See, with A1, A2, A3, you have defined one small like system, right? Like a crystal structure or lattice.
okay.
So is that volume of A1, A2, A3 or no?
Yeah, volume we define in a
Is it the
vectorial.
volume enclosed by that small space or
Yes,
not?
yes, it is the volume enclosed by this unit cell.
Okay. That is your V.
Yes, yes.
Okay, fine.
So that is equal to this base area into perpendicular distance between these two planes. It is equal to the OP.
Okay. Yeah, yeah. Got it.
So here we happen the magnitude of B3 vector is equal to 1 by interplanetary spacing of B001 planes. Similarly, we can do for B1 and B2. For B2, it is equal to 1 by interplanetary spacing between set of 010 planes. And for B1, it is 1 by D100. And simply I'm taking two vectors b3 and a2. The dot product of these two equal to 0. Why? Because we defined the vector such that b3 is perpendicular to a2. As in dot product b dot a equal to ba cos theta. So theta equal to 90 degrees. This b3 dot a2 equal to 0. Similarly, b3 dot a1 equal to 0. Why? Because b3 is perpendicular to a1 also. Similarly, b3 dot a3 equal to 1. Why we obtain this result? Because this is a consequence the way we define the vectors b1, b2, b3. We have defined this b1, b2, b3 as for our convenience so that we obtain some easy relations which can be easily related to reciprocal lattice vector with respect to real space. Here I am defining a one general reciprocal lattice vector. This is a summation of b1, b2, b3 vectors multiplied by hkl. This capital is a general reciprocal lattice vector and it is having the properties of it is perpendicular to the plane hkl in real space and it is having a magnitude of 1 by interplanar spacing between set of scale planes. Now we will see how these properties of the reciprocal lattice vector with respect to real space. So again now here I am taking three vectors a1, a2, a3. a1 not equal to a2 not equal to a3. Simply I am taking three vectors and the angle alpha, beta, gamma also not equal to 90 degrees and alpha not equal to beta not equal to gamma. Here we define one vector, this is generalized reciprocal lattice vector H, and we are saying it is perpendicular to the HKL plane in real space. Before that, I am constructing a plane HKL. It is having a intercept on A1 bar vector at point A, which is A1 by H. Then intercept at B as A2 by K, and intercept at C is A3 by K. And from the standard vectorial notation, we know that this OB bar equal to OA plus AB. And we know that the OA equal to A1 by H, the intercept it is A1 by H, and OB equal to A2 by K. Therefore, AB equal to A1 by A2 by H minus A1 by K. So this is the difference of two real space vectors. This AB vector is J, and H is a generalized reciprocal lattice vector. So I'm doing the dot product of these two. One is the difference of real space vectors, real lattice vector, and one is reciprocal lattice vector. So if the dot product of H dot AB gives here A2 bar A2 by K and KB2, it is gives rise to plus 1 and minus A1 by H plus HB1, it gives rise to minus 1 plus 1 minus 1 plus 0. So it is going to be dot product is 0. And from dot product, by standard definition of dot product, we know that the dot product of two vectors is equal to 0. That means one vector is perpendicular to the other vector. Therefore, if I'm doing here for AB, similarly I can do for BC and CA, and we will get the same result as H bar dot AB equal to 0, H bar dot BC equal to 0, and H bar dot CA equal to 0. From this, we can say that this AB is perpendicular to the H bar and also BC is the perpendicular to the H bar, and CA also perpendicular to the H bar. So this ABC is nothing but the plane HKL formed. This is the HKL plane. So we can conclude that this HKL plane is perpendicular to the generalized lattice reciprocal vector capital H. This is the one property of reciprocal lattice vector with respect to real space. And now we calculated the direction. The direction of reciprocal lattice vector is perpendicular to the plane defined HKL plane in real space. Then what is the magnitude of this reciprocal lattice vector? We have to calculate this magnitude, and from the standard dot product, we know that the projection A dot B is the shortest distance between these two vectors is going to be the projection of B bar on A bar. It is going to be B cos theta, or unit vector of A bar dot B bar. It is A bar by mod A dot B bar. Yeah, again, the same diagram I'm showing here. Here I am defining a unit vector along reciprocal generalized reciprocal lattice vector capital H. The unit vector is the vector H bar divided by mod of H bar. And we know that this capital H is perpendicular to the HKL plane. Now I'm going to find out the magnitude of this capital H. The magnitude is the shortest distance between this origin to the HKL plane. The closest distance or shortest distance is nothing but it is equal to the projection of any vector OA or OB or OC. The projection of any vector on the unit vector of capital H or general reciprocal lattice vector gives the magnitude. Therefore, this shortest distance is nothing but this is HKL plane. Again, the origin we have one more HKL plane. Again, behind this we have one more HKL plane. Set of parallel HKL planes. So these distances are closure distances nothing but interplanar spacing of HKL planes. Therefore, these closest distance or magnitude of capital H is equal to unit vector. Its unit vector times the projection of OA vector on the capital H vector. This is n cap dot a1 bar by h. As already we know that this n cap unit vector of capital H is capital H bar by modulus of capital H, and we define the general reciprocal lattice vector capital H is the summation of reciprocal unit vectors b1, b2, b3 multiplied by HKL plane. So these dot product gives here a1 dot b1, and we know that this a1 we know that b1 we define b1 it is a reciprocal lattice vector such that this b1 is perpendicular to a2 and a3. B1 is perpendicular to A2 and A3. If A1 dot B1, A1 dot B2, A1 dot B3, anyhow this B2 is perpendicular to A1, this dot product is 0, and B3 is perpendicular to A1 and A2, therefore this dot product also 0. But A1 dot B1 gives AB cos theta H by H, or 1 by modulus of HKL, because we know that A1 dot B1 equal to 1, we proved earlier. It gives us the magnitude of this generalized reciprocal lattice vector is equal to the 1 by interplanar spacing of set of these HKL planes. So as of now, we define reciprocal lattice unit vectors and generalized reciprocal lattice vector, and what are the properties and how it is related to real space. Now we need to develop some notation that capture the interaction between wave vectors and periodic crystal structure. So our final aim is to characterize a material using diffraction as a tool and to understand this concept very easily compared with real space. So for that we need to develop the diffraction condition in reciprocal lattice. As already we know that the diffraction condition or Bragg's condition in the real space is n lambda equal to 2d sin theta. These two are the incident waves and these are the diffracted waves. The extra distance traveled by wave 2 with respect to 1 is equal to the total path difference It is d sin theta plus d sin theta, 2d sin theta. The constructive inference occurs when these path difference is an integral multiple of wavelength. It's like 1 lambda, 2 lambda, 3 lambda. From this condition, we obtain 2d sin theta equal to n lambda. This is a condition for constructive inference or Bragg's condition in real space. These conditions will be satisfied by like so many set of planes. But now, what is the condition of the diffraction? Condition for diffraction in reciprocal space. For that, now here I am considering two atoms. One is at O and one is at A. This is the incident wave vector S naught. This is the diffracted wave vector, and I am extending this incident wave vector to other side S naught in the same direction, and I am projecting the S bar also backside in the other opposite direction. That's why it is minus S bar. Here in this case, I am drawing two perpendiculars. Anyhow, in the real space, we draw from two perpendicular to the second wave to calculate the total path difference. This is the two perpendiculars drawn from the O2, the incident and diffracted vectors of ray 2. Here, the total path difference is equal to the AB plus AC. The total path difference, and I am defining this OA. Here, A is a valid real space point. That's what here. Therefore, this P, Q, R are integers because A there is an atom at A. If you are defining some valid reciprocal point because of the inherent periodicity present in material, this P, Q, R are integers. This total path difference equal to BA plus AC. This BA is nothing but the projection of OA bar. BA is equal to the here from BA is equal to OD and AC is equal to OE. If BA is equal to OD and OD is nothing but projection of OA vector on S naught bar or incident wave vector. OD is equal to the projection of OA bar on incident wave vector S naught bar. So place S naught bar dot OA bar. And similarly, this OE is nothing but the projection of OA vector on minus S bar or diffracted ray. So BA plus AC equal to minus of S minus S naught dot OA bar. This is a path difference. And we know that for a path difference of lambda, there is a phase difference of 2 pi. For constructive intervals to occur, for a path difference of lambda, there is a phase difference of 2 pi. For example, for a path difference of 1 unit, there is a phase difference of 2 pi by lambda. Similarly, for a path difference of S minus S naught dot OA units, then the phase difference is going to be this S minus S naught dot OA times 2 pi by lambda. This is S minus S naught dot OA times 2 pi by lambda. This is the total phase difference now. And this vector, this wave vector, having a direction S bar and S naught bar, but it is having a magnitude of 1 by lambda. And it is 1 by length or length inverse. So this wave vector also having the magnitude of 1 by length, and we define the general reciprocal lattice vector. It is having a magnitude of 1 by length. And I'm equating these two vectors. Therefore, the phase difference equal to 2 pi into, I'm replacing S by lambda minus S naught by lambda with general reciprocal lattice vector. And upon doing this dot product, we get 2 pi HP plus KQ plus LR. But we know the condition for constructive interference to occur the diffraction is the total phase difference should be an integral multiple of 2 pi. So we obtain the relation 2 pi HP plus KQ plus LR. But the general condition to occur the diffraction or constructive interference to occur in the constructive interference to occur is the integral multiple of 2 pi. Therefore, this HP plus KQ plus LR. For constructive interference to occur, the total path difference should be an integral multiple of wavelength lambda, or it should be, and the phase difference should be an integral multiple of 2 pi. From this condition, this HP plus KQ plus LR should be an integer. If these summation of HP plus KQ plus LR is integer, it satisfies the diffraction condition or constructive inference occurs. Therefore, this S by lambda minus S naught by lambda equal to capital H vector. If it is a valid reciprocal lattice point in reciprocal space, then this HKL should be integers. Initially, this P, Q are integers because we are representing a valid lattice point in real space. If it is a valid lattice point, then these two are integers. And up to here, there is, yeah, this HKL may be anything. It may be integers or fractions. But this diffraction condition to occur, HP plus KQ plus LR should be integer. Anyway, this PQ are integers. If HKL are integers, it starts constructive inference will occur. And this is the condition for diffraction reciprocal lattice. Is it clear up to here? Hello?
Hello.
Yes.
Any doubts?
Yeah. Can you explain it again? The past one only.
First one, you mean?
Like from past, can you explain
Oh,
that
okay,
again?
okay,
Yeah.
right. 1 second. This is the condition for diffraction phenomena in real space. This is the incident beam, this is the diffracted beam. The set of parallel planes, the extra distance or the path, extra path traveled by ray 2 with respect to ray 1 is equal to the 2d sin theta plus d sin theta. If this total path difference is an integral multiple of wavelength, then constructive inference occurs. This is in the case of real space. Now I would like to know what is the exact condition in the reciprocal lattice space or reciprocal space for diffraction to occur. Here I am taking two atoms, one is at O and one is at A. I am defining one vector OA, so is that OA equal to PA1 bar QA2 or A3. Here A1, A2, A3 are real space lattice vectors or unit vectors in real space. And P, Q, R are integers. Why P, Q, R are integers means because there is inherent periodicity inside the material, or generally lattice is a three-dimensional translationally periodic symmetry. That means if you are denoting one position of a lattice with respect to another lattice, it should be integers P, Q, R because of the periodicity. Here OA, P, Q, R are integers. Like here I am drawing two perpendiculars from ray 1 to and ray 2 to find out the what is the extra path traveled by ray 2 with respect to ray 1. So here this is the perpendicular, these red lines are two perpendiculars drawn from ray 1 to ray 2. This is the equal distance, this is the equal distance they travel, but ray 2 travel an extra distance of AB plus AC. So I am calculating what is this total path difference. And we know that if this path difference is an integral multiple of lambda, then diffraction occurs. Or I'm converting this path difference into phase difference, and if this phase difference is an integral multiple of 2 pi, then diffraction occurs. So this path difference is equal to AB plus AC, BA plus AC. Here BA I'm projecting here from this one line onto S naught bar. This BA is nothing but OD. BA equal to OD, and similarly AC equal to OE. So AC equal to OE, BA equal to OD. And this OD is nothing but projection of OA vector onto the S naught bar. This is by the definition of dot product. Already I will show you one thing one more time. Yes, this is a dot product. We are doing A dot B means the projection of B bar vector onto the A bar. This distance, generally we know that this is the B cos theta, this is the B sin theta. This B cos theta, we can say this B cos theta is nothing but projection of B vector, OB vector onto the O vector, which gives the B cos theta. But this OD distance is nothing but this distance is equal to the projection of OA vector onto the S naught bar. So projection of OA vector onto the S naught bar minus into minus plus. So S naught bar dot OA bar plus again this CA. CA is equal to OE. This OE is nothing but projection of OA bar onto the minus S bar. Why? Because this is the diffracted ray direction. I am projecting backside. So this is opposite to S bar. That's why it is minus S bar. Therefore, S null bar dot OA bar plus minus S bar dot OA bar, this distance. This is the total path difference. And we know that for a path difference of lambda, there is a phase difference of 2 pi. For example, if there is a path difference of only 1 unit, then phase difference is going to be 2 pi by lambda. And if for a path difference of S minus S naught diet OA terms, or for example, if a path difference of x times, for a path difference of x times, their phase difference going to be here 1 into x, right? X means therefore x into 2 pi by lambda. Similarly, for a path difference of S minus S naught dot OA times, then phase difference is equal to S minus S naught dot OA into 2 pi by lambda. And we know that the condition for diffraction and these incident wave vector and diffracted wave vector having a magnitude of 1 by length, like what we defined reciprocal lattice vector having a magnitude of 1 by length, and it is having direction. Therefore, these are the reciprocal lattice vectors now, and it is equal to the general reciprocal lattice vector. From that, I am substituting this S by lambda minus S naught by lambda with capital H vector, and dot product of these two OA and capital H bar gives HP plus KQ plus LR. And initially, anyway, this P, Q, R are integers because this A is a valid lattice band in real space. And we know the condition for diffraction or constructive interference to occur is the total phase difference is if it is an integral multiple of 2 pi, then diffraction occurs. Already it is integral of 2 pi into some factor. If this factor is going to be some integer, then which satisfy the diffraction conditions. Anyhow, P, Q are integers. But HKL, if this HKL are integers, it satisfies the diffraction condition. If this HKL are not integers, instead of reaching a valid reciprocal lattice band, it will reach some space or some region in the reciprocal space. I will show it in evolved sphere construction. Is it okay now? Hello?
Yeah, okay, I understand now.
Okay.
Hmm.
If this HKL are integers, it will goes to a valid reciprocal lattice bands. Then this is the condition for diffraction in reciprocal space. This left side part, this is the wave vector or wave or electron wave. The wavelength we can change. The direction, the incident direction we can change. This left side part is equipment specific. This left side part can be changed in electron microscope or X-ray, XRD. This left side is equipment specific and HB, KB to LB3. This gives the information of periodicity. Because if it is reaching a valid reciprocal lattice band, it starts with the diffraction. Or else it will go to some the region in the reciprocal space. So here capital H vector gives the periodicity information in a crystal, and the left side part it is equipment specific and it is related to the waves, incident and diffracted waves. Here we are relating the waves, incident waves with respect to periodicity in a material. So this is how we define the diffraction condition in reciprocal space, which gives the relation between wave vectors and inherent behavior of material or inherent periodicity inside the material.
Ashok?
Prince, hello.
Hi, Ashok. So I was on mute. Okay. So I want to understand this. I'm not able to like fully understand the difference between path difference and phase difference. So for phase difference, like let's say if you have a sine wave, for example, if there is
Okay.
some displacement along the x, the whole curve is shifting, then we can understand it as a phase difference, right? So
Yes.
path difference is what you have shown by Bragg's law, the extra path traveled. So I'm not able to like relate both of them, like since we are not seeing any waves here, right? So how do you relate this path difference and phase difference? Equation is there, formula is there, everything is fine, but physically then give some intuition into it.
Okay.
Yeah, this way, yeah, if there is some difference, then we can say is path difference, right? Sorry, phase difference. Yeah.
Yes. For every 2 pi degrees, this is 180, right? This is 180. Every 2 pi degrees, 180 degrees is repeating. If the first wave and the second wave are in the same phase, if the second wave is starting at this point or this point, then the construct inference will occur. It is an integral multiple of 2 pi. From here to here, the phase difference is 2 pi, right? 180 degrees. This is 90, 90, 180, and this is 270, this is 2 pi. 2 pi means 360 degrees, right?
Yeah.
If it is the second wave starting at 2 pi or integral multiple of 2 pi or like 1 2 pi, 2 2 pi, 3 2 pi, then construct inference will occur. And we know this is the difference between two crust or two trough is a wavelength lambda. And this is here to here. This is 90, 90, 180, 270. Again, this is 362 pi. So path difference of lambda is nothing but phase difference of 2 pi. We can say in path difference or phase difference.
Okay, okay. Yeah, I'll ask after the meeting. Okay.
Okay.
Okay. Go ahead.
Here, how to construct a reciprocal lattice for a cubic lattice I want to show here. And here I am seeing through c-axis. I am seeing through c-axis. I can see this A and B, or I can see this A1 and A2, and this A3 vector is perpendicular to the plane of paper and board. Let us assume this A1 in real space it is having a 2 angstroms of, and because of cubic, then A1 equal to A2, which is 2 angstroms. Then how to construct a reciprocal lattice for this cubic lattice? And from the definition or how we derived or defined this b1 is perpendicular to a2 and a3. So I have to take one b1 vector which is perpendicular to a3. Anyhow, a3 is perpendicular to paper, and a2. b1 is perpendicular to a1 and a2. b1 is perpendicular to a1 and a2, such that we define in such a way we define the b1 vector on reciprocal lattice vector, and b2 should be perpendicular to a1 and a3. This b3 is perpendicular to a1 and b2 is perpendicular to a3. So I am drawing, and with a magnitude of, if a1 is having a magnitude of 2 angstroms, then b1 equal to 1 by a1. It is zero point 0.5. It is zero point 0.5 angstroms. So I am drawing two vectors having a magnitude of zero point 0.5, zero point 0.5. Generally, in diffraction data, we have in these planes. In 2D, I'm showing as lines here, but generally these are planes in 3D. And here, this is having a plane of B1 is 1, B2 0, and B3 is 0. And this is 2 0 0 plane in 3D. And here B2 is 1, B1 is 0, 0 1 0, and this is 1 1 0. Why? Because to reach here, I have to travel 1 unit along this side B1 and B2 1 1 0, and this is going to be 2 1 0. This is how we convert cubic lattice in real space into a reciprocal lattice with a magnitude is equal to 1 by a1, and we define b1 which is perpendicular to a2 and a3. This is first time I used Vesta for my presentation. Okay, we derived reciprocal lattice unit vectors and generalized reciprocal lattice vector, and what are the properties of reciprocal lattice vector with respect to real place, and what is its magnitude and direction, and we arrived a condition for the diffraction, which is in terms of v vector in the reciprocal lattice vector, which gives the crystallographic information and which gives the incident beam. So to characterize any material in TEM and XRD, we use a probe of incident beam. If you know that the incident ray and diffracted ray, and we can calculate the inherent material behavior or periodicity or crystal structure of a material by using these techniques, electron microscopy techniques. So here I'm taking this is the incident ray S naught by lambda, and with a radius of 1 by lambda, I'm drawing a circle. This is given by evolved. It is called evolved sphere or sphere of reflection. This is the incident ray. This is the diffracted ray. To reach OB, it is equal to minus of OA plus AB. It is equal to S by lambda minus S naught by lambda. If this point B is a valid reciprocal point, this is a condition for diffraction. If B is a valid reciprocal point, then only diffraction occurs. That means this is a valid reciprocal point means in this capital H vector it is a HB1 plus KB2 LB3. This HKL are integers. That means any point in the periphery or any point lattice reciprocal point which cuts or which touches the evolved sphere. In 2D it is circle, but in 3D it is sphere. Any reciprocal lattice point which cuts the sphere satisfies the condition of diffraction. And if I'm drawing one is if this is my incident vector, this is the diffracted vector, this is the something like this is capital H vector. This is the space or region in reciprocal space. This is a region in the reciprocal space. But this is valid reciprocal point. When this it is going to be valid reciprocal points means then HKLR integers. HKLR integers means there is a periodicity in the material, then only HKLR integers. Any point which touches the evolved sphere satisfies this condition, diffraction condition. These only we see in transmission electron microscopy diffraction pattern, for example. And this is and this diffraction, the points, the reciprocal lattice points which touches this evolved sphere is different for different 14 previous lattices. So that we can characterize a material by using diffraction as a tool. And one more thing, diffraction is not going to occur with respect to those points which are not touching the circle. There is no diffraction. This is the place or region in the reciprocal space. Only those points which touches the evolved spheres also diffraction condition in reciprocal space. This is how we define this derivation. Its HKL are integers. Then only we will reach to a valid reciprocal point.
Ashok, Ashok.
Hello?
Hello, Ashok. Hello.
Hello?
Small
Okay,
doubt.
okay, sure.
So here incident wavelength won't change, right? It is constant. So
Yes, yes.
how like I didn't understand how is this is different for different materials?
How this is different for?
Like this circle radius or sphere
Yes,
radius?
yes. Yeah, the incident wavelength, it is equipment specific, we can change. Okay, for a fixed incident wavelength,
Like every material will characterize with X-ray or some or electron diffraction.
okay, for a fixed wavelength.
Uh,
But if this wavelength is not changing, but this will change. The reciprocal lattice bands which touches the evolved sphere will change. Why? Because the periodicity of different materials is different. The reciprocal lattice bands, which is three-dimensionally translational vector, is different for different materials, right? The inherent periodicity is different.
yeah.
This capital H changes, HKL changes, this capital H changes.
Hmm.
Even with the same wavelength, we can characterize all 14 previous lattices.
That means S minus S or S naught will change for material.
Yes, yes. If you use the same wavelength and depending on the scattering, I mean atomic size, this S and S naught slightly will direction will change.
Magnitude may change, not direction.
But magnitude is same 1 by lambda. But which is material specific. These reciprocal lattice vectors are material specific.
Hmm.
But this one point here represents the set of planes in real space. That's what this reciprocal space is very useful. We can, instead of denoting all the planes in real space, we can say it's one point. This, for example, this is a
Yeah.
0 1 0 planes will set of all parallel planes. We can show it one point in reciprocal space. That is the advantage which is taken by a one sphere.
Okay.
And how he got the idea means generally the wave vector which are defined as k. Wave vector k is 2 pi by lambda, and wave vector k equal to 2 pi by lambda. In a harmonic equation, we know that yeah, wave as a sin omega kx plus omega t. Here k is 2 pi by lambda. Wave vector is having a dimension of 1 by length. And he thought that why to take the reciprocal lattice points, and thus that he derived this condition for the effects in reciprocal lattice.
Okay. Okay. Yeah. You can continue.
So now simple cubic and reciprocal space. This is the real space simple cubic structure, and simple cubic primitive cell and unit cell are same because it is having atom set only at the corners. It is having atom set only corners. The primitive unit cell vectors of simple cubic is in a bar direction, a bar equal to ax bar, and b is equal to ay bar, and c equal to az bar. And we define b1, b2, b3. And for example, this b3 vector, b3 is equal to 2 pi a1 cross a2 by a dot b cross c. This is volume. And this b1, b2, b3 going to be 1 by a times x bar, y bar, z bar, same. And for simple cubic, the real primitive unit cell vectors and reciprocal lattice vectors are same. But here there is a change in dimension. Here a bar is ax bar, here a bar, a star bar equal to 2 pi by a times x bar. So therefore, simple cubic and reciprocal space are simple cubic, but different dimension. Then I will show you. Yeah, generally, we know that B3 bar equal to A1 cross A1 cross A2 divided by volume. Volume is nothing but A3 dot A1 cross A2. And we know that from cross product, A1 cross A2 equal to, this is I, this is J, K. This A1 vector is AX bar, 0 y bar, 0 z bar, and A2 vector is 0 x bar, a y bar, 0 z bar. This A1 I am taking as a common, A into A going to be A square, and A1 plus A2 equal to A square times this K times 1 by 0. Therefore, this A1 cross A2 equal to A square. Here I am taking, instead of ijk, I am taking x, y, z. Then this k is going to be A square times of z bar. This A1 cross A2 equal to A square times of z bar. Then A3 dot A1 bar cross A2. A3 equal to AZ bar. And A1 cross A2 equal to A square dot Z bar. This dot product of A dot Z bar and A square dot Z bar. From the dot product, we know that this z bar in the same direction. They are having a cos 0, 1. A into A square going to be A cube. Therefore, B3 equal to A square Z bar divided by A cube. So we will get dimension of 1 by A. But generally, these 2 pi is used while discussing numerically. And like I read something like momentum space. Crystallographers use 2 pi to use it mathematically. Or generally, while defining B1, B2 itself, if you are representing numerically, then we use 2 pi. And the crystallographers or theoretical person, there is no need of usage of 2 pi. It's simply indication of it is like momentum space or real space. I don't know more exactly that. Similarly, for FCC, we know that for FCC, the
Hi,
primitive.
Ashok. Hello. Because this k vector equal to 2 pi by lambda, na? Like
Yes.
P equal to H bar K. Then there K will come from that calculation, if you see theoretically, that K equal to 2 pi by lambda. So when they are using here the momentum space, that 2 pi they are adding here.
Okay, okay.
K equal to 2 pi by lambda, na?
Hmm.
Yeah. So before you are using that 1 by lambda, 1 by lambda. So now we are going to K space. It's K equal to 2 pi by lambda. So that 2 pi only adding there here.
Okay, thank you. Actually, I
Yeah.
don't know this.
Yeah, yeah. I meant I have one question.
Yeah.
So as Ashok said, like, so let's say real space, let's say 10 angstrom. Okay. For
Yeah.
example, A is 10 angstrom, B is 10 angstrom, C is 10 angstrom.
Yeah. Yeah.
Okay, A star is 2 pi over A, right?
Hmm.
So let's say if I consider the value of 2 pi to be around 6, okay, so it will be 6 over 10, which is 0.6 angstrom. So
Hmm.
if I directly convert this 10 angstrom from real to reciprocal space, so 10 angstrom becomes 0.1 angstrom. If I write
Yeah.
2 pi by A in numerical terms, 0.6 angstrom, which is correct. In reciprocal space, is it zero point 0.1 angstrom or 0.6 angstrom?
Yeah, I'm not getting Prince. Can you tell me again? Like
See,
you see.
let's
Hmm.
say, for
Hmm.
example, in real space, it is 10 angstrom. Let's say A
Okay.
value,
Yeah. Yeah.
lattice vector is 10 angstrom.
Yeah.
In reciprocal space, according to the formula,
Hmm.
it is 2 pi over A.
Yeah.
So I consider 2 pi value to be 6.
Yeah.
Okay, so 6, it will be 6 over 10.
Huh.
Then it will be 0.6.
Yeah.
The other way is, if I directly convert, let's say A into 1 by A, then
Hmm.
it will be 1 by 10, which is 0.1. So in reciprocal space, what is the value of A, that A star? Is it zero point 0.1 angstrom inverse or zero point 0.6 angstrom inverse?
Prince, it is zero point 0.1 angstrom inverse only. This 2 pi is only for this representation. We are in some case space, that's it. Yeah, what ma'am told in condensed matter physics. We
Okay,
will not
that
Yeah.
consider
It
this
should be.
2 pi. This should be zero point 0.1 only.
so zero
1
point
by
0.1
10.
angstrom inverse, right?
Yeah.
Yes.
Yeah. Point one only.
Okay, this is for namesake, right? Or some.
Yes, yes.
Yeah.
Okay.
I think this 2 pi calculation will be there once I read K equal to that 2 pi by lambda only, na? So that for something that I will tell you maybe sometime.
Yeah, yeah, because of this question for a
Yeah.
long time, like we are not adding that value, but simply keeping y.
Yeah.
Yeah. Okay, continue.
Similarly, for FCC, the primitive lattice translation vector for FCC are three phase centers. This is 1, 2, 3. This is XY plane, half of XY plane, and A2 is half of YZ, and A3 is half of ZX. The primitive unit cell for FCC is a octahedron. And if I do the same thing like B1, B2, B3, I calculate for FCC, and it is going to be half of y plus z minus x plus z minus y, and x plus y minus z. These are the primitive lattice translation vectors of BCC in real space. Therefore, the FCC in reciprocal space is a BCC. In real phase FCC in real space, it is going to be BCC in reciprocal space. Similarly, for BCC, the primitive translation vectors are three body centers. I'm taking this body center. This is for example, this is xy plane. This is going out of z. This is x plus y minus z. E1 bar equal to x plus y minus z. Similarly, the remaining three primitive translation vectors for BCC are shown here, and the primitive unit cell for BCC is tetrahedron or rhombohedron. And if you perform and we will calculate the same reciprocal lattice vectors for these three primitive vectors, and we obtain the real lattice vectors of FCC. Therefore, BCC in reciprocal space is a FCC. Primitive lattice translation vectors on FCC lattice, but in a different length. This is here. I would like to show some definitions. What is Vignesis cell? First, billion zone, primitive cell, Bragg plane. Primitive cell is unit cell which contains lattice bands with corners only, or one lattice band. With one lattice band, we can represent primitive cell. Vignesis cell. It is the region in space that is closest to given point than any other lattice band. Here, I am considering this point my point of focus, and the region which is closest to this point For example, this region is close to the center point, then right side point, and this region is close to middle point, then top one. Similarly for left and bottom. So how we can arrive this is just joining the all nearest neighbor reciprocal lattice points. Now here we are discussing in real space. Just join the all nearby lattice points and take the perpendicular bisector. For example, the perpendicular bisectors for these two is this one, and these two, these two, these two. Why? Because these four, top, bottom, left, right, are nearest neighbor lattice points for the central atom. So these volume are in 2D. This is area. In 3D, it's going to be volume enclosed by the planes. This is Wigner's cell. What is first billion zone? First billion zone is Wigner's cell about a lattice point in the reciprocal space. If these points are in reciprocal space, the same cell is called first billion zone. In real space, we call Wigner's cell. The same thing in reciprocal space, we call as first billion zone. And before defining second and third billion zones, we should know Bragg plane. Bragg plane is nothing but the perpendicular bisectors to the line joining the origin of the reciprocal space to any other point. Here, this is one Bragg plane. This is another Bragg plane because which is the perpendicular bisector of these two lattice points. This is 3, 4. Generally, we call this our first Bragg planes. Similarly, the perpendicular bisector, the middle point, and this corner point. These perpendicular bisectors are second Bragg planes. Why? Because they are connecting next second nearest neighbor atoms. These four atoms are first nearest neighbor atoms. Yeah, these four are first nearest neighbor atoms to the central atom. These perpendicular bisectors are first Bragg planes. Similarly, these four corner lattice points are second nearest neighbor atoms to the central lattice point. Then the perpendicular bisectors of line joining these two corner point and the middle point is the second Bragg plane. Similarly, we can arrive to third, fourth Bragg plane. So what is second and higher billion zones? Already the first billion zone is formed inside the first Bragg planes. This is the central point, this is the four nearest neighbor atoms, this is the perpendicular bisector of these two atoms, this is the perpendicular bisector of this left side and middle atom, similarly for top one, bottom one. Therefore, this area enclosed is first billion zone. Then what is second and third billion zone means the area enclosed after first Bragg plane. These are the first Bragg planes. After first Bragg plane and before second Bragg plane. Here the next nearest neighbor atoms are these four corner atoms and these are the second Bragg planes. Therefore, the area in 2D or volume in 3D enclosed after first Bragg plane and inside the second Bragg plane is called second billion zones. These are second billion zones. Similarly, third and fourth. Third Bragg plane is nothing but the area enclosed after second Bragg plane. Yeah, this third billion zone is the area which is enclosed after second Bragg plane and before third Bragg plane. Similarly, third and fourth. Thank you.
Ashok,
Lakshman.
uh, you have shown the ever sphere construction slide. No? Can you please go there once?
Okay.
You explained the application of this reciprocal lattice space in terms of
How to characterize material? Yeah, as a
yes,
diffraction as a tool for characterizing material.
yes. And in case of a selected area diffraction, can you explain some little bit how we can analyze this SAD pattern in terms of this ever sphere construction thing?
Yeah,
Did you
the SAD
understand?
pattern we obtained, yeah, those reciprocal lattice bands which touches the evolved sphere
Uh,
and which follows some symmetry depending on which is face
yes,
centered, rhombohedral, triclinic.
yes.
Anyway, triclinic I don't have any symmetry like monoclinic, tetrahedral,
Mm.
and by calculating this, I think yeah, I will try in the next presentation. I think
Uh,
don't have valid resource to explain that.
like my question is like if you take a selected SID pattern,
Okay.
in SID pattern, the bright central spot will be there.
Yes.
For a cubic lattice, I am saying, if we have a bright central spot and we have a surrounding all the spots in the, and the distance between the two spots, generally we will take them to analyze this data.
Yes.
The distance between the two spots will give us what? Is it a reciprocal space or a real space?
I think it's in reciprocal space only.
Okay, if it is a
We
reciprocal
denote
space,
planes, and yeah, from that we define planes, and then we will come to the relation with respect to real space.
okay,
With that,
okay. And
that's
in that case, if that completely is a reciprocal space, the distances whatever we are measuring there between the spots, it will be in a 1 by centimeter.
okay. Yes.
Okay, okay. And if possible, you can explain the next presentation. I'll be interested in that.
Okay. Okay. I want to extend to the stay fashion application, and I don't know this, but this is after Vignesh is
Lakshman, I didn't get something you are asking. I also interested. Can you just tell
these
again?
brilliant zones and yeah, these brilliant zones are very helpful for electronic energy bands and band structure analysis. I don't know that,
Hmm.
but I want to learn
Okay.
theoretical
Uh,
understanding of elementary ideas of electronic energy bands.
uh, Actually, Minati, I'm saying about this SID pattern analysis only.
Yeah, yeah,
This reciprocal space is very helpful. This application of the reciprocal space comes into picture in SID pattern analysis.
yeah,
And when we are analyzing the data, like when we are indexing the spots generally, each
huh.
spot corresponding to a reflection from a set of planes, no?
Yeah, that too, that
And,
in world sphere,
mm,
which plane, like which point will touch, that one
mm.
will be the planes. I'm thinking that one will be that points, na? So
Yes,
peak
Ah,
will come according to that. Like you see, 1 by lambda we
mm,
are using na 1.54 copper or something. Means
mm,
I
mm,
don't know. I think like that. I am also not sure.
mm,
Like if you are using now our source is in this figure at A.
mm,
Now our source is here. So now
mm,
the radius of the Ewald sphere is like 1 by 1.54, I think. 1 by
mm.
1.54. That is the radius. So
Okay.
when that radius of the sphere will touch, like here, these points are now the reciprocal planes.
Mm,
Like some planes will be there. Let us consider some silicon or Mg3sp2 or something else. So that
mm,
where will be the planes now. So now
mm,
1.54 will be our 1 by 1.54 is our radius now. So in
mm.
that radius, when that Ewald sphere will construct and it will
Mm.
touch some points.
Okay.
So so that points now the this diffraction will happen. So
Mm,
that pattern will comes in our XRT, which is the reciprocal plane.
mm.
So it will index. Then after that we'll index it. Na? Is it not like that?
Yeah, I agree. Whatever you're saying is agree. I agree. But in case
Yeah,
of whenever we take some SID pattern,
yeah.
we cannot
That
construct a evolved sphere using the single pattern because we'll not get all the spots. We'll get only limited number of spots there.
yeah, yeah. All the spot we will not get because we don't
Mm.
know. Like late we are taking the powdered sample. We don't
Yeah.
know na how it will be. So
What I means to say is that what I asked Ashok is that
yeah.
Lakshman, for your question, I think Kishore knows more about that. How to index diffraction pattern.
Yeah,
And
I too want to know. I am not very good. I don't know all these things. Well.
I think Kishore, can you answer?
Hello.
Hello, Kishore.
Hello. Yeah.
How do index diffraction pattern, which is
No.
obtained from TEM?
Yeah. Actually, we'll know the different like that distance between the points. No.
Peter, your voice is very low actually.
Hello.
Yeah.
Hello. Are you
No,
able to
it's
hear now?
Now it's fine.
Hello. Like we'll get the distance if you get any some random points you can construct from that. Like if you know the distance between the those points,
Hmm.
using that we'll have a this lambda. Say and see. I think if you know the distance, anyhow we know the
Hmm.
input. What is that wavelength
wavelength.
from the
Hmm. Hmm.
electron diffraction thing, then we can easily do that. We'll get S and S naught is there, no?
Hmm.
Those we'll get from the SCD pattern itself, then we can construct. Yeah, if you know the distance between the 2 points for any phase actually.
Hmm.
Anyhow, we know the input wavelength, then
Hmm.
it's easy to construct this areas like this one, about sphere. But actually, the thing is, whatever if you construct, what like for what you want to construct evolved sphere, I didn't understand.
No, no. Actually, for analysis for TM
Mm.
pattern data, we will not construct the eval sphere generally. We will
Ah,
only take the distance between the spots and we will analyze the spots and we will index them there generally, in general.
yeah. Oh, you want to see what are the extra points coming onto the sphere or what?
No, no, no. I asked him like the indexing, how to index the SAD pattern using this is a reciprocal space, na?
No,
In this reciprocal, the
you get the
application of this
distance.
reciprocal space is the SAD pattern. Can you
Okay.
explain him? I asked it. No,
Yeah.
I'm not asking about the eval sphere.
Okay. Like that's like if you get two different points, just take from the what you can from the central spot, take two different points which is having two different distance. If
Okay.
you know the crystal structure, it's fine. If you don't know, also you will get the S and S naught.
Hmm.
From that we can construct, I think. But I'm not sure. Like I have to see the like I didn't know that.
Okay. Okay.
Hmm, that is it.
Yeah, Lakshman, like I'll try to see because in
Hmm.
this TM course, I think for one of the assignments I have done this distances. So I'll search
Hmm.
if I have that assignment. I'll try to send you.
Sure, Prince.
Yeah,
I'll
yeah,
be interested in that. Actually, I tried some time back, but I have a lot of doubts in that. That's why.
yeah,
Mm,
yeah,
mm, yeah.
Uh, um, Prince, hello.
yeah, yeah.
Yeah, Prince, like Ashok now explain na, this first brilliant zone, second brilliant zone, and all that thing. In that, some paper I saw like they are telling band unfolding. In that band on unfolding, they are taking the thing like that supercell. They are fully explaining in fast brilliant zone something. Can do you know that? What is that actually?
I don't know about the exact terminology we're talking about, but only
Hmm.
one thing I do know is whatever this relevant zone is there in our DFT calculations also we use to sample our case space. So we don't even consider the first Brillouin zone. We consider the wedge, which is a something called irreducible Brillouin zone, the smallest portion in the first Brillouin zone, which can represent the entire Brillouin zone. So maybe that band edges you're talking maybe within are
Something
those at
called
some
band unfolding, something called that.
okay, okay. Yeah, if you have something specific, you can just mail me. I'll
Yeah,
see.
that is called something band unfolding. What they're doing, they are taking that, they're explaining everything in the past Belanjun, nothing else. So something they're doing
Yeah,
that
yeah.
I
They
don't
might
know.
not do
Yeah.
in the first Brillouin zone, but the
Hmm.
smallest portion of the first Brillouin zone.
Yeah. That I'll just message you if you're finding. Just
Yeah,
explain
yeah.
me. Yeah, and Prince, you were asking me. I think that that k is 2 pi by lambda. I think for why they are taking now when we are taking this like some sine wave or cos wave, like sine kx minus omega t. So x will be in distance, and but in sine kx minus omega t, it should be in radian. So what they are doing? That's why they are taking k equal to 2 pi by lambda, because this lambda will be there, x will be there in distance. Like if you consider some wave function like sine kx minus omega t, So for that only they are taking k equal to in multiple of 2 pi to adjust that.
Okay, I'm even more confused. Maybe sometime later explain
Then
that.
okay, later. Okay. It's nice today.
And Ashok, your talk is very good, man.
Yeah.
Any suggestions for next time
Uh,
presentation?
Uh, Good presentation, Ashok.
It's nice.
Anyone else have any questions, or you can?
I think Prince, you can stop the recording.
Okay.